we run an application, in this case that's Lightwave, and we stand there with a bucket catching all the OpenGL calls that fall out of the application, right? And then we scoop them into ViewPerf, we tweak them a bit, and essentially what's going on here is a replay of a frame's worth of OpenGL calls. And the good news there is that what this benchmark gives you is real-world OpenGL streams that came out of real-world applications with real-world models being pumped as fast as possible through your graphics driver, over your bus, and out to your hardware. Now that's a reasonably useful benchmark. Now, every single one of these applications, when it's doing graphics, does it with a single thread. So therefore, doing multiple threads at once and multiple graphics contexts at once doesn't match a lot of applications out there. Does that explain?
Yeah, so you're presenting a real-world look at the application, not necessarily the maximum that the machine can do, because the machine could handle more threads than that.
It's more complex than that. Okay, for another minute or two.
Yeah. So you're still going to do green code.
Yes, I will.
Yes. Just, we're going to wrap it up in about 5.
Okay. All right. So imagine an application, and I'm going to pick on Pro Engineer as an example. Okay, Pro Engineer's OpenGL code was written about 170 years ago and is not the most efficient. And all the engineers who did it aren't with PTC anymore. And so their graphics core, while adequate, could be better. It uses a lot of immediate mode, which is where what's happening, if you imagine you're rotating the model on the screen, you have incremental rotations. And for every increment, it's redrawing. So as long as you're dragging the mouse, it's redrawing. Every time it redraws, it goes through a loop in the code. And with an application like Pro Engineer, as it goes through that loop, there's a lot of CPU side stuff where it is traversing the entire scene. It's working out where it stored the triangles that represent the scene. That's called a tessellation. And then eventually it gets around to emitting those triangles to the OpenGL pipeline. And so finally the drawing can happen. That means that some large amount of this circuit through the loop is spent on the CPU side and not the graphics side. So just imagine, say, you spend 80% of the time in the CPU and 20% actually doing true OpenGL on the hardware. Well, if you put in an infinitely fast graphics card, the thing would only go 20% faster, right? And so you don't get much scaling, and that's what we observe if you look at the results. In fact, if you look at the results posted on the spec website for the Pro Engineer Wildfire benchmark, we're all posting with FX 580, FX 380, because there's no point specifying a more expensive card because it doesn't go faster. Now, when you take Pro Engineer's OpenGL output and you put it into ViewPerf, your loop is all concerned with pushing OpenGL. So you don't have this extra CPU side bloat. So therefore, it's a much more efficient exercise in getting the OpenGL, which was the OpenGL we captured from Pro Engineer, out to the graphics card. So you will see better scaling because now the graphics card is not waiting for all this CPU side stuff every cycle. Does that make sense?
Yes.
Wouldn't you see minimal differentiation between machines with single and multiple core processors though?
Minimal. For ViewPerf, yes.
So
because it's a single thread thing, right? The aim of ViewPerf is simply to take real-world OpenGL captured from real life and push it out to the graphics pipe as fast as you can, and thereby characterize professional graphics doing professional OpenGL. Workstation class work.
but it doesn't sell Z800s. I mean, it sells.
Well, sure it does.
Well, except it's going to be the same for a
Well,
6-core
yes,
system
but
versus 24.
But the Z800 is our only workstation that can take the Quadro 6000. But see? So, okay, need to wrap up over here. Put your hand up if you're familiar with the Dream Color display and don't need to hear anything else about it.
Oh.
I usually tell people that if I want to train them on just the Dream Color display, it will take about 5 hours because just getting your heads around the concepts is really, really hard. I've done it a few times for new hires here who need to have responsibility. This is Maya, by the way, a trace from Maya. I'm going to kill it. And there we are. That's my sexy CSS. I did all the prettyfying of that web page. So anyway, so I've already given you this indication here that this car is looking hugely different either side of my bezels here. This monitor is the ZR24W, which is our most recent, current, performance 24-inch monitor. This one's a Dream Color monitor. And right now, I've got these set in a mode where the color is way, way different. So, a few things to say. First of all, this red color is almost unique in the display industry. There is nothing that you can do to this monitor to generate that red. And the reason is that this monitor has fluorescent tubes for its backlight, just like these things, whereas this monitor has red LEDs and green LEDs and blue LEDs, and the red LEDs are somewhat this color, slightly modulated as you go through the pixels, but the hot reds that you can get from that thing are entirely down, or mostly down, to the colors of the LEDs in the backlight. Now, so comes the question, which one of these is correct? My answer in this case is, well, probably this one, because I'll bet the person who was setting up this paint material was using this kind of monitor and not one of these. He may really have wanted to have this color, but it wasn't available to him. So this is probably what the designer intended. No problem, I can just push some buttons here and I can change this monitor to conform to a specific color space, in this case sRGB. Pow. Now, this monitor is a good value monitor. It's about $425 list price in the US. Great monitor, great visual performance. It is designed to be very close to sRGB in its color performance. This one lists for around 2,000, I think, which sounds expensive, but if you think of competing products, which are up in the 5, 7, 8, 15,000 range, this one is a steal. What we're seeing now is complete, guaranteed, highly accurate compliance with sRGB. So this one's designed to be about sRGB and should give people no surprises. This one, because I chose sRGB from this menu, is factory calibrated at high precision to be exactly an sRGB reference monitor. Or I could choose a different color space, like Adobe RGB. Let's say I'm doing digital photography. In this case, you won't see any difference unless I choose green. Let's choose that one. Close that. And you can see on this side the green is rather yellowish green, whereas this one's a much more, well, I don't know, a green. And sure enough, if you look at the diagrams that differentiate sRGB from Adobe RGB, you'll see that Adobe RGB extends into green primarily. So the point of this monitor is not that you can do totally hot, eyeball-burning reds, although they're cool for certain audiences. They think that's the amazing thing. The point of this monitor is that if you know what you're doing, it will deliver super accurate color for whatever computational color-critical workflow you happen to have. Whether it's product review, whether it's video editing, whether it's broadcast, whether it's animation and film compositing and coloring, this monitor can do it all.
Any last questions for Dan? If not, we're going to make the walk back for lunch.
I should make one final comment.
Okay.
If you've been photographing this, your camera will not manage to capture that red.
Yep.
And then when you look at it on your monitor back in
It'll
your
be even
office,
worse.
It won't capture. You just won't see it. Well, I'm going to...
Dan, thank you so
Thank
much.
you.
You're going to walk with us, right?
I will, yes. I'll be a few minutes late. I just want to turn off some monitors.